You're welcome to ask any questions about, well, not the labs, but mainly on the exam that will happen on next Monday. And the exam will be comprehensive, starting from the very beginning of the course to the very end. So I'm sure you can ask all kinds of questions, any questions from the past lectures to owner. Yeah, and I know a lot of you are having troubles with labs right now. I'm sorry about that. There are a lot of bugs that are creeping up. This is only the second time that we're giving this particular instance of the class, so a lot of the code hasn't been fully stabilized yet. And I think Andrew has been instrumental in finding a lot of the bugs that were not uncovered last year as well. So hopefully we'll get that fixed up. And so I really apologize for the things that have been happening, but we'll try to make sure that you don't get penalized by implementing a behavior that we specify the handout, or some basically discrepancy to the bugs that we've actually introduced. So we'll give you as much credit as we can for that, so that you're not penalized. And so the labs, the final lab will be due next Friday, and so 1 week after the exam. There will not be any extensions for that because we have to start grading and inputting the grades immediately after we receive your labs. And the exam will be on Monday. And so yeah, I will be holding lab sections today, and all the TAs will be holding lab sections until next week. So you can certainly drop by to one of our office hours or lab sections to get help on finishing lab 7. So today, Andrew?
Just a quick question.
Yeah.
Do we need to get the lab checked off? Like, we're turning it in on Friday.
Yes.
Do we need to go?
Yes. So right now, like with everyone using up their late days in an asynchronous manner, the checkoff dates have almost become meaningless because some people have been submitting their labs almost at the last day of checkoff due date. So as long as you get checked off before the next Friday for all your labs, you'll be fine. So don't worry about it. So yeah, so today I was thinking of just, go ahead.
Does that include lab 7? Or?
Yeah, lab 7.
Sorry, lab 7.
Yeah.
So we have like until the second, like 2 weeks from
Well,
today.
so lab 7 is due next Friday, isn't it?
Right.
But I mean, are you guys going to be around the week afterwards? I mean, it's
Like I'm going to be gone like within a couple of days after taking this final.
Oh, are you?
Yeah.
Okay.
Yeah, I was planning on like.
Oh, that's why. Okay, so you're saying that you want to turn it in remotely, and so that means you can't get it chalked off physically. So yeah, I think we'll be able to accommodate that. But I'll just talk with Professor Mutlu, but I think you'll be fine. I mean, you don't have to stay around for that.
I was under the impression there were no checkoffs for lab 7 because
We're not going to have checkoffs?
that was what
Is that what Justin said?
yeah, that was what Justin said.
Okay, so, okay, maybe not then. Maybe we won't have checkoffs, but I'll clarify this. So, yeah, so we've been kind of unclear about, we've been kind of making calls on our feet about the labs because everything's been shifting, yeah, with the travel arrangements and stuff like that. So, yeah, okay, great. So I was thinking of going through midterm 2 today. If anyone else wanted to look at something else, would that be helpful? So I think it'll be helpful review for the finals because the material that was covered during midterm 2 will also be covered during finals, and it's actually going to help you study for the finals a lot because if there was a concept that we feel that a lot of the students didn't get, it might be possible that we might ask it again during the finals in a different form. So yeah. So unfortunately, my laptop is wonky and I can't get the dual screen set up, so I'll have to look at the screen with you. And so I'll start. Does anyone have want to start from a particular question within the midterm 2 that they were burning to know about?
I had a question about the warp question.
Okay.
Or just like more wanting to talk about like a little bit because I didn't really understand the solutions.
This one, right?
Mm-hmm.
Okay. And your question was?
So it was about problem B.
3.
Just like how you get that 1 out of 64 when you have the 67 over 256, and kind of like, just like generally like how to go through this.
Okay.
Because there were a few
Okay, so why don't we just start from the very beginning then? I mean, right? Yeah. So, so basically we have a GPU, which is SIMD machine, and you have this following thread segment, which is running on this GPU, and one thread executes one iteration of the loop. So what you're doing is you're taking the loop, unrolling it, and taking different iterations and mapping to different execution cores as like cores within the GPU. And okay, so there's 64 SIMD lanes in this GPU, which means that you can probably you can execute 64 iterations at a time. So how many warps does it take to execute the program? So yeah, so you have, what is that? That's 1 million, right? 2 to the 20. You have 2 to the 6 number of SIMD lanes. You divide it by it, and that's how many warps it requires. So a warp is the gang of 64 guys that are executing parallel. So 1 million divided by 64 threads per warp, and you get that number. It's simple. So B, when we measure the SIMD utilization for this program with one input set, we find that it is 67 over 256. What can you say about arrays A, B, and C? So if you look at it, each iteration is guarded by an if statement. So the iteration itself, the execution is only done if the ith element of A is larger than 0. So what this means is that if you think about it, let's see, find that it is 64. Say about arrays A, B, and C, one every 6. So because the SIMD utilization is less than 1 to begin with, it means that not every iteration executes, it is executed actually, right? So then that means that the if statement evaluates to false for some of the warps, and so let's see, SIMD utilization 64. So how do we calculate this? We find that it is.
Yes, this is where I was having issues. Understand the solution.
Yeah. Okay. So it had to do with the fact that so given that let's say that a warp is if the element ith element of A evaluates positive, then that means all the 3 additions will be executed, right? If it's not, it won't be. So compared to when it's executed, when it's not executed, so okay, so measure the SIMD utilization. So I think the key point here is I think decoupling 67 into 64 and 3, because if you think about it, it's so 64, 64, 1, 64, 1, 64, 1. Jason, do you remember this problem? SIMD utilization? 1 out of every 64. Okay, so why don't we draw this out on the board? I think that would be better. So, okay, so the iteration says you have, each iteration looks like this. So if AI is larger than 0, do something. Do an add, do an add, an add. So, okay, so the utilization is given as SIMD 256, which means that you have, so you have a, let's see, you have, so if all of, so if AI evaluates always to true, then your utilization will be 256 over 256, right? given that all of AI is greater than 0. So what would happen if AI, none of AI is 0? If all of AI is less than, then you would get, so, well, you don't even need a 256 factor here. You can just say, for a given warp, because each warp consists of 64 threads, none of the warps are executed, and so on and so forth for all the different warps that are in the program. If it's larger than, this would be 64. But if all of them are less than 0, then it means that it would be 0 over 64. So we're somewhere in the middle. But the key problem is, I think the key aspect of this problem is that it's 256. And so let's see. What this is saying is, so we're somewhere in the middle here. And if you decouple this, what this is saying is, I think I got this. So I think what's happening here is you have warp 0, warp 1, warp 2, and warp 3. And each of them consists of 64 threads. And I think, so what's happening here is, let's see, 164. So, okay, let's first backtrack. And given that we know that 1 out of 64 warp, 1 out of 64 elements of element A, let's see if it's actually evaluated to this. So given that, so what would happen is if only one of the elements within A is larger than 0, then that means that within warp within the 64 threads within warp 0, 63 of them would not execute, and only one of them would actually execute, and so on and so forth. So given this, I mean, what's the utilization here? The utilization is, so the thing is, okay. The thing is, how many instructions are there per iteration? So there are 4 instructions, right? You have the conditional. You have the 3 additions. So if you have, so that was where the 64 was coming. So the 4 multiplier was coming from. So if you think about it, so for 63 threads, they would only execute the conditional and bail out, right? And for the single one, it would execute 4 instructions. So what would happen is, for 1 out of 64 guys would execute 4 out of 4, and these guys would execute only 1 out of 4. And since there's 63 of them, you multiply it by 63. And if you add these 2 up, then you get this number. Am I right? I think so. I have to weight it somehow, right? So, yeah. So these guys have quarter utilization, but there's 63 over 64 of them, right? And and for these guys, so there are 1 out of 64. Did I get this right? So that would come down to, wait, so is that right? 256, 4, and, aha, there we go, yes. Great. So I think we were a little bit tricky about the fact that the 4 instructions are actually, instructions, right? So they take up instruction slots within the core. And so what can you say about arrays B and C? Well, I guess nothing, because they're always, nothing's actually conditional on arrays B and C. They're always executed. They're just data inputs. So is it possible for this program to yield a SIMD utilization of 100%? Well, yes, I guess. I mean, like I said before, if all of the elements of A are larger than 0, then of course. Uh-oh. There you go. Okay, if yes, what should be true about arrays A, B, and C for SIMD utilization be to you're 100%. So all of A's elements are greater than 0. Or, so the second part that was tricky was if all of all of A's elements are less than or equal to 0. So if you go either way, the funny thing is, so less than 100% utilization happens when there's an imbalance, right? You have a warp and 64 threads, and if some threads within the warp decide to go one way, whereas some of the other threads go the other way, then you have an imbalance because there's some guys want to do more work and some threads want to do less work. So it's obvious that if all of A's elements are larger than 0, then they all do all the work. And the work consists of doing the 3 additions that's guarded by the if statement. But on the other hand, if all of them were actually less than 0, then this is kind of weird because what happens is all of the threads within the warp decide not to do the work. So they only evaluate the conditional and bail out, which means that there is no imbalance, right? So the SIMD utilization during that given time. So what happens is the total time to execute the loop becomes much shorter, in which within this time, the only thing that the program does is evaluate the if statement over and over and over again. So it has a utilization of 100%. So that was kind of the tricky second case. OK, so if no, explain why not. Well, I guess there is no possible reason. Is it possible for this program to yield a SIMD utilization of 25%? Could this be possible? 25%. What would that mean? What kind of imbalance would you need to have within the thread system? SIMD utilization of 25% means that some threads are executing. So you have 4 instructions. Instruction 1, 2, 3, and 4. On average, what you're doing is you're executing only this guy, right? But if you're executing only this guy, then that means that that's a scenario, the inverse scenario, in which everyone executes this guy and says, this is false, I'm not going to do any of this work. In which case, the utilization becomes not 25%, but becomes 100%, right? That was everyone with me so far? Yeah, OK. Great. So, OK. Yeah. So that was that. And anyone have any other specific question that they want to start off with? I can just go through the entire exam. How about memory scheduling next then? This was my question. So memory scheduling. So this was kind of here. The specification for memory scheduling that was in the exam was a little bit different from the specification we gave out for Lab 6. And one of the reasons that I made this question was I wanted, so the specification in Lab 6 was a very simplified version of DRAM. And I just wanted to give a taste of what actual DRAM operates. So this problem started off with kind of giving you slowly building up enough background to be able to solve the question that come at the very end. So so in the very beginning, so so as you can see, it starts by drawing the command and bus timelines when you have row-buffer conflicts, right? So as you know, for row-buffer conflicts, you need pre-charge command, you need an activate, you need a read, and then so on and so forth ad nauseum if you have a steady stream of row-buffer conflicts. And you can see that, in the lab, we said that each command takes 15 nanoseconds. I forget, was it 200, 150, I think it was? But here we said it was 10 nanoseconds, which is actually much closer to what's done in real systems. In real systems, it's about 12 or 13 nanoseconds. And so after a read command is sent, after a certain period of time, the bus that corresponds to the read command comes back over the data bus. So the question was, I mean, given this steady stream, I mean, what is the data bus utilization or the bandwidth of the memory system, given that you have a steady stream of row-buffer conflicts? And the answer was very simple. What you do is you take the data bus, the timeline for the data bus, and see how much of it is filled in. You can see that at every 30 nanoseconds, the data bus is utilized for 5 nanoseconds. And during that 5 nanoseconds, 64 bytes is sent. So equivalently, this could be, you can say that what this is saying is every 30 nanoseconds, send 64 bytes. So what's the bandwidth? The bandwidth is simply 64 byte divided by 30 nanoseconds. And we asked you to state this number in terms of gigabytes per second. And all you had to do was add, multiply 1 billion to the denominator and the numerator, which would be very simple. 64 gigabyte divided by 30 seconds. So something 2.x. But for some reason, this calculation was very difficult for a lot of you. Some people thought nano was not 10 to the minus 9, 10 to the minus 6. And there's all these weird stuff going on. But at least, as long as you got this part right, I gave you full credit. So that was that. And so the second part of the question for Robot for Conflicts asks, to increase the data throughput, the main memory designer is considering adding more DRAM banks to the single DRAM channel. So given that all the banks, however number they are experiencing back-to-back robot for conflicts, what is the minimum number of banks that is required to achieve the maximum data throughput? And this problem can also be solved very graphically. The goal is to basically look at the data bus and come up with the minimum number of data bus transfers that are required to fully populate it so that you achieve the maximum bandwidth. So as we saw before, every 30 nanoseconds, you consume 5 nanoseconds to send one chunk of data. So in theory, what you need is 6 banks so that all the data bus, if you have 6 transfers back to back, then you can fully populate the data bus. Everyone following so far? So what would happen in that case is you would issue an activate to one bank, and 1 cycle later, 1 nanosecond later, you would issue an activate to a different bank, to a different bank, to a different bank, to a different bank, to a different bank. So across 6 banks, you can all the latencies are kind of overlap partially, so that they can mostly do everything in parallel. So okay, so now the other question that we're asking is for robot for hits. This is the second part of building up the background for solving the questions that come up later. So in this case, there's a single bank, and there are consecutive robot for hits to it. And as before, I'm kind of straying away from the Lab 6 specification and saying that what actually happens within DRAM chips is that a robot for hits are actually pipelined in terms of the latency. So it's not as if you issue a read command, wait for the full latency, wait for the data to come back, and then issue a read command, which is I think what happens in this simulator right now. But in real systems, what happens is you can overlap this latency, pipeline it, so that if you have multiple robot for hits, the latencies are mostly overlapped. So the problem says that half of the latency of the read can be overlapped with the guy in front or the back. And you can see that this leads to the data bus being fully utilized. So here we ask, what is the memory throughput in this scenario? So if you can imagine having a long stream of row for hits, then like I said, the data bus is fully utilized, which means that you're transferring 64 bytes not every 33 nanoseconds, but every 5 nanoseconds. So, which means your bandwidth is 64 bytes divided by 5 nanoseconds. That was the answer. Simple. So and the next question asks when this maximum data throughput is achieved, when the data bus is fully populated, utilized, that has a single DRAM channel in a single DRAM bank, what is the bottleneck that prevents the data throughput from becoming even larger? Circle all that apply. So when you're accessing DRAM, there are 4 resources at hand. One is a bank, one is a command bus, one is the address bus, and one is the data bus. I'm asking, in this scenario, which of the 4 can actually be the bottleneck? And as you can see, in this scenario, it's impossible for the command or the address bus to become the bottleneck. Because if you think about it, for every request, you're sending just one command, aren't you? The read. And it just takes up 1 nanosecond in the command bus or the address bus. On the other hand, sending one read makes the bank busy for 5 nanoseconds, 5 times that amount. So the command and address buses can never be bottlenecks in this scenario. So if you if you circle any of those, you got points deducted, I think a lot. On the other hand, the data bus is the bottleneck because, like I said before, it's fully populated. But an interesting thing is the bank is also the bottleneck. The bank is designed so that the amount of latency that it can pipeline between 2 row for hits is exactly the same amount that is required for the data bus, for 64 bytes to be transferred over the data bus. So what I'm saying is that the bank and the channel are balanced. So they become the bottleneck at the same time. So if you circled both bank and data bus, then you got full credit. If you circle only a data bus, you got most of the credit. So that was the answer. So then another question you can ask is, remember how I said for this particular system, when you have 6 banks, you can theoretically fully populate the data bus bandwidth. But is there any, even in that scenario, would there be any benefit in having more banks? Like for example, like 8 or 16 banks? Anyone?
Just one channel.
Well, actually, there is a benefit. The reason for that is, so what happens is, so for example, let's say you have, I don't know, maybe like 16 cores on your system or something, 8 cores, and they're generating, they happen to generate 16 requests at the same time, right? And what happens is, so if you have a lot of banks, the probability of any 2 requests going to the same bank is reduced. So, although the data bus latency cannot be parallelized, what you can do is you can still parallelize the activate latency and the pre-charge of each bank. So yeah, that's kind of a side note. So now building on these 2 questions, on this background, using the parameters as above, the final part of this question asked, for different memory scheduling policies, what would be the memory stall time of when the state of the request queue is like this in the memory controller. So this is the request queue in the memory controller, starting from the oldest request that came the first, which goes to bank 0, row 0. And the second request also goes to bank 0, row 0. Third request the same. The fourth request goes to bank 0, row 7, and so on and so forth. And there's a distinction between the requests depending on whether it's shaded or not shaded. The shaded requests are from thread, I think, let's see, for thread 0, and the unshaded requests are from thread 1. And so given this request queue, the question then asks, okay, so the question then asks, not this guy, the stall time, the memory stall time of threads 0 and 1 for 3 different scheduling policies. The first is the first come, first serve. Second is the first ready, first come, first serve. And the third is the parallelism-aware batch scheduling policy. So, so the correct answer to this question is actually very complicated. You have to think about conflicts in all the 4 different resources. But I don't think anyone actually went through that level of detail. And what I think a lot of the students did was just to look at the conflict at the banks while ignoring conflicts everywhere else. So, so if you did that, and if you did it correctly, we gave you full credit. So, but if you tried to model some effects due to command address or data bus contention, we gave you credit for that as well. So yeah. So so let's go back to this request queue. It's actually very simple. If you're talking only about, so what the question basically boils down to, if you're going to think only about the banks, then it's just an ordering problem, right? So so for the first come first serve, it's very simple. So what you would do is this is the mental model that that you can have. So you can have bank 0 of 3, bank 2, bank 0. And you have 3 requests to row 0. This goes to this goes to row 0, row 0, row 0, and row 7, row 0. Maybe I should just write the numbers. 0, 0, 0, 7, 0. So you have 5 requests queued up at bank 0. And at bank 1, you have requests going to 9, 4, 0. So this, if you had kind of a per bank request queue, this would be the state of the memory controller. So, so what would happen here? For a first come first serve scheduling policy, okay. So you can see that this is the last request of thread 1, and this is the last request of thread 0. And these are all requests of, I think, was it thread 1, right? Yeah. These are all thread 1's requests. These are thread 0's requests as well. And so you can see, if you're considering only the bank conflicts, then B0 is the critical bank for the first come first serve policy, because by the time you get up to here, these requests would have been served, So if you don't think about command, address, and data bus conflicts, for our purposes, these guys are served in parallel at one shot. Shoop. Done. And afterwards, these get served in turn. So, so basically, it's a matter of how fast can you actually serve these two guys. So if you look at the latency, the first guy, since the bank, all the row buffer in the banks are closed, this requires a pre-charge, which takes 10 nanoseconds. And then you need to issue a read, which takes 10 nanoseconds. Right? This guy requires an activate and a read. This guy is a row buffer hit, so it requires only a read, 10 nanoseconds. This is an activate, read, read. The guy only requires a read as well, 10 nanoseconds. But once you get here, since it's a different row within the bank, you have to pre-charge it, read it, activate it. You guys can read this, right? So, and then afterwards you have to do it again. Pre-charge, activate, read. For this guy. So this is for the first request. The read is for the second request. The read is for the third request. Pre-charge, activate, read is for this guy over here. And pre-charge, activate, read is required for the last guy over here. And since, if you count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times 10 nanoseconds, 100. But you have to remember to add the trailing 5 nanoseconds for the data bus transfer itself. Because if you think about it, well, the read command itself takes 10 nanoseconds. But after the read command is consumed and processed by the bank, it takes 5 more nanoseconds for the data to actually come back, right? So if you just remember to actually add that at the very end, you'll have been fine. If you just forgot that, you just gotten 1 point off. But yeah. So that's the first come first serve policy, in which none of the requests are actually reordered. Everything is scheduled in the order that you came in. On the other hand, for the first ready, first come first serve scheduling, first ready, first come first serve scheduling policy, what would happen is the memory controller would be smart and say, oh, look at this. If I reordered request to row 7 and request to row 0, I could have a better row buffer hit rate. So this would be 0, and this would be 7. And you would do the same thing all over again, except that you would have one less pre-charge activate because the 4 guys are row buffer hits. So that's that. That was what the first ready, first come, first serve policy would do. And the last question, parallelism aware batch scheduling, I think most people got that wrong. It was actually it's one of owner's very favorite papers. It's his idea. And it's kind of disappointed. And the idea there is, so if you think about it, all of T1's requests are queued up here. It's unhindered by any other requests. And as long as we're servicing 3 of its requests in 3 other banks and unhindered, why can't we take one of its requests that's just stuck behind here and just pull this guy up? just this one guy, right? That's the idea. So in this case, what would happen is the reordering would take 7 and put it all the way in the beginning and serve these 4 in parallel. So what this would do is this would drastically reduce the stall time of T1, drastically, but at the expense of T0. T0 stall time would increase by a little bit, but I mean, it's relatively speaking, it's not by that much. It's like going to a grocery store and you're stuck behind a person who is shopping for this big barbecue. You know, the shopping cart is filled with lots of items, and but you have friends that happen to go to different, you know, checkout counters, and you only have like a carton of milk. Your other friend has eggs. So in that case, it would be better if I were to kind of, you know, squeeze in front of the lady who's shopping for the barbecue and, you know, quickly go out and check out with my friends, right? Counter level parallelism and get out of there. But for the lady, I mean, you know, checking out you know, just the milk is nothing in her perspective, right? So that's the idea of parallelism aware batch scheduling. So the key concept of parallelism aware batch scheduling is that it's thread aware. It actually distinguishes requests from different threads. Before, first come, first serve, and first ready, first come, first serve, when they were get the request, they only looked at the request in terms of whether it hits in the row buffer, whether it came first or not. That's the only thing that it looked at. But parallelism aware batch scheduler knows which requests belong to the same team. This is team 1 and this is team 0. And it tries to basically take all the team's requests and service first in front of the other team's requests or thread. So that was that. OK, so should we move back to the very beginning? Were the appropriate questions easy enough that I don't have to cover them? They were kind of, you know, very close-ended questions, right? So yeah. So I'll just kind of scroll through them. And if you have any questions, you can stop me.
Explain that one.
This one?
Yeah,
The bulk synchronous parallel processing?
Yeah.
OK. So we were kind of joking to ourselves that that was par BS, and this is BS par. So we had two par BS questions, sort of. So assume we have parallelized a program into 8 threads. Each thread performs the exact same computation on different part of a very large data set partitioned across the threads. OK. Seems like an embarrassingly parallel problem. The threads communicate at the end of the parallel portion by synchronizing at a barrier. After that, a single thread runs and aggregates the results generated by each parallel thread. Okay? Many parallel computations are structured in a similar way in a model called bulk synchronous parallel processing. You run this program on a multi-core processor with 8 cores, where the only shared resource between the cores is the memory controller and the DRAM system, and measure the following execution time in seconds for each thread. There is a single memory controller, and it employs the FRFCFS request scheduling policy. Okay? So different threads have different execution time. They're mostly similar, except for thread 3, it seems. What could be 3 reasons T3 takes longer than the others? The first one is given to you. 1, interference in the memory controller that delays T3 more than others. Okay. So 2 and 3 say load imbalance and input set dependence. So what this says is, it's bulk synchronous parallel processing is a very fancy name, I think, for a very simple concept that we all know. It's otherwise known as, I guess, MapReduce is, you know, it's known by multiple names. So let's take a very simple job that you want to do. You have an array, int a, that has, like, I don't know, 1 million elements in it. And you want to sum across all the elements within array A. And a simple way to do it is partition the array into smaller subarrays and offload the partial sums to different threads, right? So you can have thread 0 that adds from A0 to A 99, and you could have thread 1 going from starting off where it left off, 100K, until 199, 9999. Okay, so on and so forth, right? So you can have different threads computing sub-sums and aggregating all of them together. So, okay, so, but it seems that you've partitioned the data equally, right? So each thread gets 100K elements, and does this work? So ideally in this scenario, there shouldn't be any imbalance. Everybody should finish the same time, except, and it also used to be the case here because, I mean, barring all these second order effects, I mean, all the additions are very simple operations. But let's say, for example, that, so partitioning, this is static compile time partitioning, right? You're dividing the work at compile time. But what could go wrong? I mean, this is a very simple partitioning, but sometimes what can have is more difficult partitioning problems. So for example, let's say the TAs are grading homework, right? And so we take an equal number of students' homeworks and start grading them. But it turns out that there's a student, you know, maybe some students, you know, wrote very terse answers, and some students wrote very long answers that take a long time to parse. Right? In that case, even though the TAs started grading the homework at the same time, when they end, they would finish different times. So that's the load imbalance aspect of things. And this actually happens a lot. Like for example, I mean, when you have like for example, a server, like a Google server, it doesn't know when a request comes in, like the YouTube server, it tries to partition them, I guess, by like round robin, you know, assigning the requests to different computers. But maybe one request might happen to, you know, request like a video that's not been viewed by many times, so it's not cached, so it has to go through the hard disk drive. So, yeah, this is what you call, you know, load imbalance due to task partitioning. It's kind of a fancy word. That, and another thing is input set dependence. So, well, I guess the third thing is kind of almost, they're kind of mirror things of each other. So input set dependence just tells you that it's one of the things that could cause load imbalance. So, so for example, if the data set, you partitioned it, and maybe it's not doing a subsum, but maybe you're just taking 10 numbers, giving one of each number to each thread, and asking the thread to factorize it. You know. But one number happens to be very large and it's very difficult to factorize. In that case, the thread, when they actually synchronize at the barrier, they would do so at very different times. So there, yeah, 2 and 3 are not strictly orthogonal things, but I guess kind of sort of related. But okay, suppose you would like to tackle the first reason. How would you modify the memory controller to improve the program's performance? Okay, so given that all the 8 threads are cooperative, they're not competing threads, right? You want to make sure that they arrive at the same time. Otherwise, one thread, the slowest thread, would lag, you know, would make all the other threads wait. That was kind of similar to the warp imbalance problem, where we had branch divergence in the SIMD warps, the first problem that I talked about. So this is the problem. The way to solve this problem is basically find the slowest thread and speed it up. That's it. You want everything to complete at the same time. That's your best solution, because otherwise the slowest thread would slow every guy either down. Okay, so now say you have another program that works in the same way. You run this program on the same multi-core processor and measure the following execution time in seconds for each thread. Okay, every thread takes 10 seconds or 10 units of time to execute. How would you change the scheduling policy in an attempt to improve this program's performance? Okay, explain correctly. So, okay, how would you schedule this attempt to improve the performance? So it makes this way. Program that works in the same way. Why would this speed up the program? I do not understand. What's the difference? Oh, okay. Oh, this is, okay. I think, so I guess this could be a solution. So what this is saying is, I'm not sure if this is really inferable from the information given here, is that I guess all the threads are kind of running slowly? And could there be a way to actually expedite the execution of different threads? And the question was, and the answer was, what you do is you try to emulate PAR-BS somehow. Remember how if different threads request ends up, oh yeah, no, the answer was given. The answer, enough condition was given. So the controller was set to execute the FRCFS, and that's the bad thing. So what happens is you have 8 threads going to memory controller, and it would have requests queued up in some random manner. A, B, C. And the controller, when scheduling it, would have no idea which request came from which thread, and it just looks at it and tries to maximize roll for hits. But maximizing roll for hits is not the best thing to do sometimes when you have multiple threads. What you want to do is make sure that everything kind of goes in parallel, right? All requests from the same thread go out in parallel. The next request from the next thread all go in parallel, and so on and so forth. So what this answer is trying to say is we want to increase the bank level parallelism of requests. And this could be done in one way by saying, okay, my queue is really clogged up. What I'm going to do is I'm going to pick one thread, a random thread, and say, hey, your requests can all go right now. And the thread is happy. Yay, and all its requests go. And then the controller picks another thread and say, it's now your turn. And its requests all go next, and so on and so forth. So this is a way of increasing parallelism. Yeah. So why can your proposal improve performance? Reduces interference between threads by ensuring each thread's memory requests are serviced in parallel in different banks. Can your proposal hurt performance? Yes. So like I said, it's a sensitive trade-off. So sometimes in the question I had before, question 5, the question was set up so that even though you batch up all the requests of thread 1s and service them first, the overall roll for hit rate didn't get hurt by too much. But it could turn out to be the case that if you order things based on thread ID and try to serve all the requests from the same thread at the same time, you might reorder things in a bad way that you're completely destroying roll for locality. So in that case, what will be happening is you'll be gaining parallelism, but losing so much roll for locality, roll for hit rate, that your overall performance might actually go down. So yes, that is a potential possibility. OK, so pointers and cache enigma. So did people have questions on the cache enigma question? I think the average for this was actually pretty high, I think. If not, I'll pass. We covered GPU SIMD. We covered memory scheduling. So I guess we have 2 questions left. So we have the code optimization question. I think I think I can cover this really quickly. So this question was not designed to be hard, but I think many people felt it was hard. So so you have this code, which consists of 5 basic blocks. Basic block 0 is usually referred to as the loop preheader in compiler terms, I think. So there are only 4 basic blocks within that are part of the loop. And you have this particular program only has 5 or computer has only 1, 2, 3, 4, 5 type of instructions. And the latency or the execution number of cycles it takes to execute each instruction is listed on the table right there. So a move takes 1 cycle, addition 2 cycles, multiplication 5 cycles, and magically this computer is able to execute conditional branches and unconditional branches immediately. So given this program, so the first task at hand was to actually calculate how many cycles does the machine take to execute the assembly program when A and B are initialized to 0 and B at the beginning. So A and B can be considered to be the input to the program, and F can be considered to be the output to the program. And this was required so that you kind of have a feeling about how the program works. So you can then propose optimizers on top of it. So this program at a high level is A and B are playing catch up, right? So every time you go through the program, you either go left or right. If you go left, so what's happening is if A is in basic block 1, it's asking is A larger than B. If it is, B needs to catch up to B, A. So you go to the left basic block 2, and you increment B by 2. If not, it must be that A is smaller than B, so A needs to catch up to B, right? So A is incremented by 1. But if you think about it, this game is entirely rigged in the favor of A, because A gets a special leg up in basic block 1. In basic block 1, it's always incremented once, right? So they're playing, A and B are playing a game of catch up, but it's kind of rigged in favor of A. So B needs to be incremented more often. So this entire program is biased toward BB1. Got it? Okay. BB2, I'm sorry, the left branch. So yeah, so this is, I mean, I wrote it down a very long solution, but that's all you need. You need to know which direction the branch resolves to, and just calculate how long it takes for A and B to reach a particular value. So, and each iteration, thankfully, takes the same number of cycles. So you just calculate how many iterations you took, 22 cycles per iteration, add 1 cycle at the very end for initializing f at the loop pre-header, and you get 177. Not too hard. So you decide to make simple modifications to the program to reduce its execution time. The optimizations involve only removing, modifying, or moving some of the already existing instructions. You may not move each out of the loop, and you may not add completely new instructions. So this problem actually has multiple valid answers. But if you, so the very simple solution that we thought of was, so there are these 2 instructions at BB2 and BB3 that are redundant. You can remove them and move them down, but this is not actually going to affect your execution time because they're executed in both paths anyway. But what actually was, what we're looking for was what's called, this is mentioned in class, it's taking just the multiplication and reducing multiplication by 2 and reducing down to addition, right? So multiplication takes 5 cycles. 2 times A is equal to A plus A. It's an algorithmic identity. If it's an integer, it might not be true for other data types, but it's always true for integers. So if you can change the multiplication to an addition, which is also called strength reduction in compiler terms, you can reduce execution time. So there were some other people that came up with other clever optimizations that we haven't thought of. I think that's always the danger of giving you an optimization question because people might come up with very creative answers, and you got credit for those as well. So how many cycles does the machine take to execute the optimized assembly program? This is very similar. Just go through in 8 iterations and take the renewed number of cycles to execute your optimized iteration. So okay. So now, kind of the fun part is now we ask you to optimize the program using the concept of superblocks that you learned in class. So, so people, I think a lot of people were confused about superblocks, traces, and hyperblocks and stuff like that. But the thing about superblocks is it was also given in lectures, but you can just think of superblocks as duplicating the tail. So if you have basic block here, goes here, goes here. And let's say you know that this path is really hot, right? So ideally, if this guy didn't exist at all, you could do some weird stuff only for this path, doing awesome optimizations. But this guy, which is rarely taken, screws up your optimization. And this gets worse if this happens to be a very complicated, long basic block, right? Let's say it's doing a ton of complicated stuff, which might screw up the optimization that you're planning to do for this hot path. So what superblocks does is, OK, you know what? We're going to duplicate the tail. We're going to decouple these 2 guys by making it like this. And this would be your superblock. And you can, because these are kind of independent now, right? Independent, you can do all kind of crazy stuff inside within the superblock, which you couldn't have done if these 2 guys would have merged at the end. So, here, so you can see that there's 2 tails now. There's a BB2 tail basic block, which follows BB2 basic block, and there's a separate BB3 tail, which follows the BB3 basic block. So due to the fact that the value of A does not change if you go towards the left direction, you can actually do what is called constant propagation in compiler lingo. You can just take the very top calculation you did for 2 times A and reuse that to assign into, you don't even need that because you can just reuse the values you had before. So you can remove the unnecessary computation, which is 2 times A or A plus A, and use the value you've already calculated and substitute for the redundant variable that you would have calculated. So that was the answer. And so at the very end, well, I guess, yeah, so we also ask you to execute the time required to execute the optimized program. And here, since it takes different number of cycles to go through this path and this path, because this path is more optimized now. So now you have to be taking into account of the fact that this is taken 5 times, is taken 3 times, and calculate appropriately. Before in the calculations, we always assume that each iteration took the same number of cycles, regardless of which path we took. But that's not the true for superblock optimization because the path the optimization is path specific. So okay, so F and G I think it confuses a lot of people. If you had to use traces to optimize the program instead of superblocks, would the execution time increase, decrease, or stay the same compared to E? Choose one and briefly explain why. The answer is that actually the execution time would increase. So what traces try to do is instead of duplicating the tail, it adds fix-up code to each path. So remember, this was the original code, and you wanted to do crazy optimizations here, which would affect the correctness had this path been taken. So what you do is you add fix-up code like some, like for example, I guess here or here. So at random places, you add fix-up code that undoes the results if the wrong path was taken. So that's basically the concept of traces. And it's I think for a better explanation, I think you should look at the lecture notes. And because of this fix-up code, you increase execution time. So what's the trade-off? For superblocks, you're increasing your instruction number, right? You're making your code size bigger. It's bloatier because you're duplicating the tail. But on the other hand, since now these are kind of independent paths through your instruction stream, you can do separate optimizations. On the other hand, traces don't try to duplicate as much. They just take an existing path throughout the control flow graph and try to optimize it better. And when you take the wrong path that goes strays away from that a bias path, you add fix-up code to fix up for the optimization that you made. And the last question was, if you had used hyperblocks, which sound more fancier than superblocks, to optimize the program instead of superblocks, would the execution time increase, decrease, or stay the same compared to E? Choose one and explain why. This also increases the execution time compared to E, which was the superblock optimization. And the distinguishing feature of hyperblocks is that it uses predication to resolve stuff. So the problem, this is also covered in lecture notes, is that one of the problems with superblocks is that if a branch is hard to predict, then you can't coalesce them into a path because a branch is not really biased. So to get rid of that, a hyperblock was an optimization proposed saying, okay, let's not choose one path to optimize it for at the beginning, but if we don't know which way it's going to go, let's fold it in as part of the same block by using predicated execution. So what this was saying is that, for example, remember how this was the original graph that we had? And here, the conditional that decided which direction we're going to go was this statement which asked, is A larger than B? And do something here, do something here. So hyperblock would try to make this a single block by saying, if this is an X instruction and Y instruction, how it have, if A is larger than B, do X. If A is not, then do Y. And these are predicated instructions that we saw before in class. But so this allows you to fold everything into what is sort of like a basic block, but because there are still dependencies of that are produced by these instructions X and Y, you can't do that optimization where you can assume that A wouldn't change, because you don't, before you actually do the predicated instructions, you don't know whether the value of different variables will change or not. So this doesn't actually affect, this actually prevents you from doing the optimization, which would have enabled you to gotten rid of the redundant computations. So these are kind of counterintuitive. I think a lot of people put down decrease for both questions, but it was not the case. Superblock was the best for this particular trace. So, okay. So now I guess we have the last question. Jason, can you actually cover this quickly? Yeah. The last question, I had a question. Yeah.
Yeah, so this question, people didn't do too well on this question because it was the last one, and I guess people didn't have time to do it because the previous parts were too long. And so this question actually isn't hard. It's just you have to walk through it cycle by cycle, make sure everything is correct. So let's start. In the solutions, I included a table that tells you cycle by cycle what's going on. So if you compare this with your own answers, you'll be able to see what you got wrong here. So it's hard to see. Okay, so in the first cycle, load 1 is issued, and then since it's a miss in the cache, because the problem says that all loads are misses to simplify things, so this load causes run-ahead execution mode to be entered, and you can see the second to last column here means tells you that run-ahead mode has been entered. And inside run-ahead mode, you just execute the following instructions like you would do normally. So you do the adds. The adds take 2 cycles, and then you do the load. You load the second. You issue the load. You issue the second load to memory, and then so that takes 1 cycle. The loading takes 1 cycle, and it returns in, I believe, 9 cycles. Yeah, so in cycle 4, the load 2 is issued, and in 9 cycles it returns. So in cycle 13, you can see that load 2 finishes. The same reason, load 1 takes 6 cycles, so it's issued in cycle 1, and cycle 7 is finished. So that's how you calculate how and when the loads finish. So returning to the first run-ahead execution section. In cycle 7, load 1 is finished, and therefore in cycle 8 you exit run-ahead, and then you start executing from the first load, which gets you to cycle 8, which lets you re-execute the first add, because previously the first load caused you to enter run-ahead. Is this like clear? Is it easy to understand? Because you basically just run through everything and make sure that you don't get anything wrong. Basically, whenever you have a miss, you enter run-ahead, and inside run-ahead, you run through everything, following all the instructions that are following. And then after the cycle after the miss gets filled, then you exit run-ahead, and then you continue running from the beginning. So here, if you look at this table more in detail, I tell you which instructions are additional run-ahead instructions and so if you add those up, you'll get the correct number of additional instructions. So the first question is, how many cycles does the program take to run in run-ahead execution? And the number is 40. Wait, the first one is without run-ahead execution. So that would be very easy. They're all stall the entire processor, and then that's why it takes 42 cycles. That's very easy. I think most people got that correct. Now the second question is, how many cycles does it take with run-ahead execution? And it's 27 over here. You can run through your own and see. Most people got this correct too, but then some were off 1 or 2. It depends on, I think it depends on like off by 1 errors. Like some people thought the run-ahead execution ended earlier or ended later, 1 or 2 cycles, and that's what caused the discrepancy. And the third question is, so that's 27. Third question is how many additional instructions were run? So in the first run ahead execution section, 6 were run, and then 3, 3, and 2. So that's 14 altogether. Let's see what else. Now assume that exiting run-ahead execution incurs a penalty of 3 cycles. This is because, you know, in run-ahead execution, everything is speculative. So when you exit run-ahead execution, you would have to like restore the registers to its original state, and that's why here in this problem it takes 3 cycles. Since there are 4 times where you enter run-ahead and exit run-ahead, the total number of cycles is 27 plus 3 times 4. So 3 cycles for each of the 4 run-ahead execution cycles. Sections. So that is why this is 39, yeah.
So if you're going to be waiting for like 3 cycles or whatever extra,
Yeah.
wouldn't your loads and stuff come back early enough that like you maybe wouldn't have to go into like run ahead execution for one of the later ones?
What?
You almost have to redo the whole table.
What do you mean? You mean in this problem?
Yeah, like if you go back up to the table.
Yeah, sure.
I mean, I don't remember.
Mm-hmm.
Like if you come back, maybe it was only if it was 4, but if you come back from run ahead execution and you have to wait like 3 cycles, then the load may finish that would have put you into run ahead for like the second one or whatever. Or maybe.
Which exactly? Do you?
I
Can you
don't
see this?
remember, like, if it actually happens or not. So I could be wrong, but instead of like just making that like assumption that they're all gonna have like the 3 cycle.
Well, I mean, in this problem, it's just.
You have to like make sure that like your load wasn't pushed back further because of your cycle.
We didn't actually think about that for this problem. Basically, the reason why we had this penalty was we want you guys to understand that it's not free exiting run-ahead execution. I don't think we.
Yeah, I'm not sure that I'm saying exactly like what I meant to be saying.
I see. Well, first of all, in the real world, I mean, there are tons of optimizations, and this problem might not reflect all the optimizations, of course. So this was an easy version where we just add 3 cycles to the end of each, and have you compare the differences. If you actually want to talk about this after class, you can. If you have any details, we can do that, of course. If you think there's any problem.
Yeah.
Yeah, but basically, we just wanted you to understand that when you exit, you have to incur 3 cycles of penalty. Is that good? You want to look? It's fine. Okay. We can talk about after class B1. Yeah. So this is easy too. At least how many cycles should the run-ahead exit penalty be so that enabling run-ahead execution actually decreases performance? Well, this is possible because if you incur 3 cycle penalties every time you exit run-ahead, then you will be doing useless work, and you might even take longer time than if you did not use run-ahead altogether. So 42 cycles is the number of cycles you need without run-ahead, and 27 is with. So you want to get 27 over 42, so 27 plus 16 is 43, which is over 42. And since we have 4, you have to have 16 penalty cycles in total, and since there are 4 run-ahead execution sessions, you would need at least 4 cycle penalty for each section. And that's assuming you add a flat rate of 4 to the end of each run-ahead execution session. Now for F, circle the run-ahead execution periods that were, circle the instructions that cause run-ahead executions. So this was easy because in the problem we specified that each load was a miss, and thus each load would always cause a run-ahead execution session to run. Now, for each load that caused the run-ahead execution period, tell us if the period generated a prefetch request. So this question is asking basically whether or not each run-ahead execution session was useful or not. Did it generate prefetches? So for load A, it generated 2 prefetches, so that's good. For load B, C and D, no prefetches were generated, and they were for different reasons. For B, you had overlapping run-ahead execution sessions, which meant that the run-ahead session, that the instructions that were executed in load B's run-ahead were basically the same as load A's run-ahead. So in load B, the run-ahead the instructions were already executed and the prefetches were already generated by the previous run-ahead session, which means that load B was basically useless. Load C, dependent loads, that was because in load C, when you wanted to generate a prefetch for load D, the register was not ready yet. So that's why there was a dependent load. So if we go back to load C, where's load C? So cycle 19, so at the end of cycle 19, load 3 finishes, and at the end of cycle 19, load 3 finishes. But in cycle 19, we were trying to generate a prefetch for load 4 inside the run-ahead execution session. But then load 4 is dependent on load 3, and that's why you could not generate a prefetch in this, the third run-ahead session. And that's why the third run-ahead session was useless. And the fourth run-ahead session, basically, you had no loads at all inside the run-ahead in the subsequent instructions, and therefore there were no prefetches generated because there are no loads. So for G, we were asking you how to mitigate the inefficiencies caused by entering run-ahead sessions when they were useless, basically. So load A was useful, so that's fine. Load B, what you can do is, if there are only a few cycles are left before the miss is filled, you can basically just choose to not enter run-ahead execution session, because if you enter, the load will be filled very soon. So you will have to incur additional penalties if you enter run-ahead and then exit within a few cycles. For load C, the dependent loads, you can actually predict the value of cache miss address loads. This is talked about in detail during the lecture. Professor Mulu actually mentioned a paper that talks about predicting the addresses of dependent loads, and that could be used here. In load D, you can also predict. During the lecture, he said that you can actually predict whether or not a run-ahead execution period will generate useless prefetches or not. So if the prediction determines that this run-ahead execution session would be useless, then you can actually choose to not enter it. Okay, so we're almost done here. H is if all the useless run-ahead execution sessions were eliminated, how many additional instructions would be executed? So if you remember from the table, the first run-ahead execution session executed 6 additional instructions, and that's the only one that's useful. So if we had all these optimizations put into place, only the first run-ahead execution session would be running, and therefore there will be 6 additional instructions. And the later 3 run-ahead execution sessions will not be entered. So how does this number compare previously? Of course, it's less because you're only doing 1 run-ahead execution session and not 4. Here it asks you if the penalty is 3 cycles, how many cycles it takes with the penalty for run-ahead execution. It's basically 27, which is the earliest cycle count for run-ahead with no penalties, plus 3 because you only enter run-ahead once, so it's 30. And it's obviously less. And the last question is, how many? What should the penalty be for run-ahead execution with penalty to take more time than just not using run-ahead at all? Again, the numbers are 27 to 42. You want to get 27 plus something to be over 42, and the something is 11 at least. So, and there's only 1 run-ahead execution session, so that penalty has to be at least 16 in order to get run-ahead with penalty to take more time than not using run-ahead at all. So basically, this whole latter part of the question wants you to know that the penalty for run-ahead execution might make it not worth it to do run-ahead at all, because there's a big penalty at the end. Now, most people didn't get this question right because most of the answers depend on the second question. The 27 cycles is very important. If you did not get that, then you will not be able to get most of the other questions correct, unfortunately. And also, as I said, most people were off by a cycle or 2 for the 27 because of off by 1 errors. So if you look at this graph carefully, you'll be able to find out where exactly you got this question wrong. So I guess that's it for this question. Is there any question? No? Is that it? Okay, I guess that's it for today. Yeah. Good luck on the exam.